So we're going to solve this problem using the convolution formula, which we've already quoted. It's this. Now the PDF of y is equal to 2y for values between 0 and 1. So I can immediately replace the limits of integration here with 0 and 1 because the PDF of y is 0 outside those limits. I'm going to leave the first term unchanged for the moment. It's the density of x at z minus y. And then I can replace the fy of y by its value between 0 and 1, which is 2y. Now I need to do something with this. And this is where it's critically important that you remember that the density of x is not equal to 2x everywhere. It's only equal to 2x between 0 and 1. So we've been told that the PDF of x is equal to, now let's just emphasize it, it's 2x for x values between 0 and 1, and it's 0 otherwise. It's not always equal to 2x. And the thing we're interested in here is the value of this. The density evaluated at z minus y. Well, that depends on both z and y. Okay? And so one thing we can do immediately is we can say that, well, fx evaluated at z minus y is equal to, I'm going to rewrite what I have here, but I'm just going to replace x everywhere by 2 z minus y. So 2 times z minus y for 0 less than z minus y less than 1 and 0 otherwise. So this is telling me when this expression can be replaced by the value 2 into z minus y, and it requires this to be true. Now what I'm particularly interested in here is the relationship between z and y. So I'm going to add y to this condition here, and that's telling me that I need, if I add y all the way through that inequality, it's y less than z less than y plus 1. And that condition must be met for this expression here to be replaced by 2 into z minus y. Now we noted in the first video that z is the sum of two numbers between 0 and 1, and therefore it has to lie between 0 and 2. And we also know that we're dealing with y values restricted to between 0 and 1, as we've already reflected in the limits. And I find it useful when I'm doing a problem like this simply to draw a picture of what's happening. So I'm going to draw a picture of this. I'm going to have a z-axis up here. I'm going to have a y-axis along here. There's y0, there's 1, there's 1 for z, there's 2 for z. So y has to be between 0 and 1, z has to be between 0 and 2, so I really have to be somewhere within that rectangle. But I've also got this additional constraint here. Y has to be less than z. So if I draw the line on here where z is equal to y, that's that line. And now I'm going to draw the line where z is equal to y plus 1, which is just that straight line shifted up by 1 so that it goes through these points here. That's the line z is equal to y plus 1. And I need values of z which are above this line and below this line. So I need to be effectively within this region here. What is this region? Well, it's the region, the combination of z and y values, so that z minus y will lie between 0 and 1, and I can then replace in the integral the fx of z minus y by the value 2 z minus y and not by the value 0. Now we noted before that the density for x plus y will be 0 for z values less than 0 and above 2. So we know that we're dealing with a z value here between 0 and 2. But the problem is that the limits for y will depend on whether z is between 0 and 1 in this region here, or whether it's between 1 and 2 in this region here. You can see this formula here tells me the size of the density of x plus y at a fixed z. So it's telling me the value for a particular value of z. And when I evaluate the limits here, the limits I put in will have to reflect the particular value of z that I'm using. So you can see that if z lies between 0 and 1, then I can replace fx z minus y by 2z minus y, provided y lies between, let's say that's my z value, between 0 and 1, then y will have to lie in this region along here. So y has to vary between 0 and this value here, which is indeed z, because that's the line where z is equal to y. But if z is fixed between 1 and 2, say the z value is here, then you can see that I can't have too small a value of y. I have to start off with a value that's here, and I can go up to 1. So the value of y, to be inside that region where that density is non-zero, I have to go between this value. Now this is the line z equals y plus 1, and so to go backwards, y is z minus 1. So if the value here is z, the value of y here is z minus 1, and it goes up to a value of 1. That's the range of values that I have for y there. And what this means, therefore, is that I can now write this as being one of two things, depending on whether I'm talking about a z between 0 and 1. Let's start off with that one, or a z value between 1 and 2. So if z value is between 0 and 1, y has to go over the range 0 to z. So this integral becomes the integral from 0 to z of, now I can replace the fx by 2z minus y times 2y dy. And here, for z fixed between 1 and 2, the y value must go from z minus 1 up to 1. Again, the same integrand, 2z minus y, 2y dy. And that's the crux of solving this problem correctly, getting these limits correct, and perhaps a diagram would really help you in doing that. The actual integral here is pretty straightforward and we don't need to worry about it, but say you have the answer. This is 2z cubed over 3. That's the form between 0 and 1, and this integral is equal to 4z minus 2/3 of z cubed minus 8 over 3. These two expressions are equal at 1, so it doesn't really matter whether you have a less than or equal to here or here. And that's the solution of the problem using the convolution formula. Method B, we'll use the distribution function method. And I just want to give you a hint about how to get started with that. You have to get the distribution function, that is the probability that x plus y is less than or equal to z. In the statement of the problem, if you read it carefully, you'll see that you're just told that x and y have the same PDF, but they're not linked in any particular way. And to solve this problem, it really helps to pair them up into a bivariate random point. So here I have a random point in the plane. X is the x coordinate and y is the y coordinate, and I'm referring to it as a P. with a double line, which is reminding me that it's a two-dimensional random variable. So if I do a graph of this, x is going to vary between 0 and 1, and y is going to vary between 0 and 1, and they're independent, so I'm going to get a point in the unit square. It won't be a uniform point in the unit square because the marginal distributions are certainly not uniform. The distribution for x, for example, the marginal distribution for x is triangular. It's equal to 2x. It looks like this, the marginal distribution for x. It's the line 2x, and so x is more likely to be near 1 than it is to be near 0. And of course, if I look at the marginal distribution for y, if I happen to draw that along here, this is the density for y. If you look at it on the side, y is also nearer to 1, and so if I looked at a realization of this point, I'd have a larger number of points near to the top corner than I would down in here. And what I'm looking at is the probability that x plus y is less than or equal to z. The nice thing about putting x and y together into a point is that you can identify a region now where x plus y is less than or equal to z, because, for example, this is the line where x plus y is equal to 1. So if you wanted to calculate the probability of x plus y being less than or equal to 1, you would just have to integrate over this lower triangle. But you need to do it for all possible values of z. So that's how to get started. So try to solve this problem using method B, the distribution function method, and then come back to the next video in this sequence.